Thanks very much for coming. So we are delighted to welcome here a candidate for our faculty position in astronomy. So I'd like to introduce Joey Rodriguez, who is currently a, let me get it exactly right, Future Faculty Leaders Postdoctoral Fellow at the Harvard-Smithsonian CFA. He started out at Rutgers as an undergraduate there, like one of our esteemed grad students. And so he's been actually known something about salt from all the way since he was a wee babe. After he went to Rutgers, he went on to George Mason to do applied physics. Is that right? Or
applied engineering physics.
Right. So he did a master's degree there, and then went on to Vanderbilt to do his PhD in astronomy. And from there, he moved on to Harvard, where he is now. So he is involved in a lot of really exciting efforts to find and characterize exoplanets, and also understand the disks inside of which those planets form. And so without further ado, I'll let him take it away.
Well, thank you very much, Ryan. Can you guys hear me? All right. I don't think I needed the mic that well, but so I'm really glad to be here. I'm going to talk to you today about two separate types of objects. Specifically, all of it is umbrellaed under one theme, and that's understanding how planets form and evolve. And to do that, I'm going to talk about two specific types of objects: extrasolar planets and occulting disks. There we go. And so again, this whole thing, my whole research is kind of umbrellaed under this one topic of trying to understand how planets form and evolve. We've known about the solar system for a very long time, but we've only known about the planets, extrasolar planets, for about 2 to 3 decades. And in those 2 to 3 decades, we've shattered every planet formation theory that we had, and we're still trying to figure out how planets form and evolve, asking the same questions we did when we found the first planets in the early 1990s or late 1980s, who you talked to. And so a lot of my work, though, is using publicly available data. A lot of it comes from the KELT survey, which I'll get into what that is. But most of these are publicly available. The ASAS, the Harvard photographic plates that go back about a century, the Catalina WASP surveys, and then our big amateur professional global follow-up network that confirms our exoplanets as well. And so I like to break my talk into 2 acts, kind of like a play, and I'll have a quick pause just to make it feel that way. But I'm going to talk about transiting planets, and I'm going to do a little bit in reverse of how you do planet formation. And we're going to talk about the evolved planets first, and then I'll kind of end with what we're doing for the young stars and the debris disks and try to understand the actual formation of these planets. So, just to kind of give you a quick recap, one of the biggest methods to find planets, and probably one of the most informative methods, is the transit technique. It's a very simple concept. You just look for the periodic occultation of a planet going in front of the host star, and from that you get a relative size of the planet to the star. And everything I'm going to tell you about the planet is relative to how well you know the star. There was a big conference about, I think it was 6 months ago. It's called Know Thy Star, Know Thy Planet, right? And it's a very important concept because as well as you can characterize the star, bless you, is how well you can actually understand the planet. So please keep that in mind. But the transit technique doesn't tell you it's a planet. It just tells you that something's occulting the star that is consistent with the size of a planet. However, small stars can be consistent with the size of a planet. And so to rule out small star versus planet, we also use the radial velocity technique. You're looking for the relative wobble of the star as the planet goes around due to the gravitational pull. And that actually tells you the mass of the planet relative to the mass of the star. And therefore, we can confirm whether it's a planet. Now, a decade ago, this was as simple as it got. It's gotten a lot more complicated over the last decade, and I'll get into what I mean with that in a little bit later. So, I love this plot. This is just, first of all, look at the year at the top right. All right, so we are not, like, this is 3 decades we've been in this field, okay? But this shows you all the exoplanet discoveries over time and where they land on this mass period diagram. And so this is just going to play through. And what you'll see, this is 1989. This was Dave Latham's first substellar object. 51 Peg comes in. The pulsar planets are down here. This is all the radial velocity surveys, the transit surveys, Kepler launches. You can actually hear there's a little bit of a sound that I have it on very low back there. But what you end up seeing is that we've probed some of the population, but not all. Okay, so we now know of over 3,000 planets. We have thousands of more candidates, and TESS is expected to drop 20,000 on us. So we're going to be saturated, but the thing is, we are still only probing a very small part of the parameter space. Specifically, we're not really probing long period planets because transit surveys have not been running that long. The radial velocity surveys have, but astrometry is going to fill this in. And then we are starting to dig down into the Earth-sized planets with the success of Kepler and the future success of TESS. So, what has happened over the last few decades is that the field of exoplanets went from pure discovery, just find as many as you can, and that was kind of the idea of Kepler, just find as many as you can, and you could do statistics and try to understand demographics. But what has happened is that we have over 3,000 planets confirmed, and so therefore the field has kind of made a dramatic shift away from just pure discovery, and now we're trying to understand demographics and also try to find those rare, extreme, valuable targets that allow us to understand key questions about planet formation and evolution. And so rare, extreme, valuable is what I'm going to talk about today. I realize that's a little bit of an opinion-based term, but this is where KELT comes in. This is also where the K2 mission, the repurposed Kepler mission, has come in. So, what is KELT? KELT's the Kilodegree Extremely Little Telescope. I can see the smiles around the room. I know, it's adorable. But what it is an all-sky photometric survey by two 42-millimeter cameras. Okay? So we have KELT North out in Arizona. We have KELT South out in SAAO, so we're about a half a mile from SALT. And we're doing exoplanet survey of bright stars. So we're targeting V of about 8 to 11. The idea of that 8 to 11 was to fill in the gap from the previous radial velocity surveys, as well as the previous transit surveys. And also, when you have a very bright star with a transiting planet around it, you can get a very high signal and noise and do atmospheric characterization. And your signal and noise is directly correlated to how well you can characterize the atmosphere. So bright stars are very good for that. These were two planets that we discovered a few years ago that I led. And just to give you kind of an idea, this is how the telescope works. We feed in a list of fields. Each field is 26 by 26 degrees. Our pixel scale is 23 arc seconds. I'm not making a mistake there. Those are the terms. Our PSF is about an arc minute. So blending is a big issue. But the telescope just reads in a list of fields and continuously observes whatever is available. And therefore, what we have is 5-year baseline, 6-year baseline in the south, a 10-year baseline in the north, with a 30-minute cadence. Just going to tell you right now, you can do a lot of science outside of looking for extrasolar planets with a 10-year baseline and a 30-minute cadence on bright stars. And I'm going to go into some of the other science that we've done. So this is our field map. Each one of these squares is corresponding to one field from KELT. The color is when they were added, so each color kind of corresponds to how long of a baseline that we have for these observations. And again, I mentioned this field of view, and I'm going to show you what 26 by 26 degrees really is. I think it's kind of impressive. But this is the main point of the survey. It was only $60,000 to build each of these telescopes. Okay? So therefore, they're very inexpensive, but they've been very productive. So we have like the cheapest cost per planet from any survey. I don't know if that's really bragging or not, but and so you have a long baseline, but you also, again, we're trying to find those targets that are optimal for atmospheric characterization, because that's the next step, is understand the atmospheres and try to understand the differences between the planets we're finding. And then we've kind of opened up a new field, and we're finding planets around massive, rapidly rotating stars, which was not possible 5 to 10 years ago, but it's been possible through the development of new techniques like the Rossler-McLaughlin effect and Doppler tomography. And I'll get into what Doppler tomography is in a bit. So, what is 26 by 26 degrees? It's a lot. It's a big part of the sky. If you guys know your constellations, right, it fits in perfectly into one of our fields of view. This is what the moon or the sun would look like in one of our fields. I've caught, for you guys who know your southern hemisphere, I've caught both Magellanic Clouds in one field. It took some finagling, but I did it. So you're covering a lot of sky at one time, which makes your reduction incredibly tricky because of spherical geometry. Essentially, first of all, we have a 30% difference between the center of the image to the edge in sense of brightness, but because of spherical geometry at the corner of our images, it's a little tough to see, but you can kind of see that they become little angels, like angel wings, and that's due to the light being kind of like smeared out in a circular pattern. And even given these weird shapes, we are able to do 1% photometry on stars in D of 8 to 11. Now, KELT does not discover planets. KELT discovers candidates, and I think that's a clear distinction to make. Our follow-up network, which is all small college observatories, you're looking at these 8 to about 1 meter class telescopes, amateur astronomers, these are small college observatories, very similar to what you guys have on the top of this building, are doing our photometric follow-up, and then we also have spectroscopic follow-up from bigger facilities. And so this is really the backbone of the survey that has led to the confirmation of 22 planets and of dozens and dozens of variable star science as well. And we also have a little bit of time on the LCO and the Skynet networks as well. Now, we're in astronomy, we're in academia. Everything is based on what you did, not what you could do. And so this is kind of the success of KELT. This is the 20 discoveries that have been publicly announced. In fact, all 20 are published now. We've had about a handful of discoveries from the south. We've had most of our discoveries from the north. It's been running about twice as long. We've even had joint fields where both telescopes observed and found planets out of that. There are 2 planets that are not published, KELT 22 and KELT 5. You will see KELT 22 way before you see KELT 5. It's been there for a while for a reason. It's a tough target. But we have 22 discoveries now. Now, we are not a mission like Kepler. We're not going to find thousands. We're not going to find hundreds. But we're going to find a few dozen, and those few dozen are going to be very amenable to atmospheric characterization because they're orbiting bright stars, they're giant planets. Now, I'm going to go through and kind of walk you through how do you discover an exoplanet. And I think this is kind of fun to go through because I'm going to show you the example that had a lot of press and is actually a Nature paper led by Scott Gowdy. So we start out, this is the KELT light curve. So this is 10 years of data phase folded to a day-and-a-half period. As you can see, you see this little, clear transit-like signal. But all that tells us, again, is possibly that something is occulting the star we think. Because of the big pixels, because of the big PSF, there's a lot of blending, and therefore a nearby eclipsing binary can cause and mimic the same signal. So once we have this candidate, we send it off and we get photometric follow-up from our amateur small college network. And so these are all, if I recall correctly, this is a 12-inch, this is a 12-inch, I think this is a meter, this is a half meter. I mean, these are not particularly big telescopes, and these people get 1, 2, 3 millimag precision on these observations. It does help that this star is incredibly bright at 7.5. And again, I realize that is a relative term and an opinionated statement, but it's bright for my science. Now, if you were to just bin this all together, you can kind of clearly see the nice transit signal. This is about 7 millimag. Because the star is so big, the star is an A0 at 10,500 Kelvin, this corresponds to almost 2 Jupiter radii. So it's a very big planet. Again, this doesn't confirm that it's a planet. We have to get radio velocity measurements. Now, I realize this is a very tough signal to believe. This is a 6 sigma, I believe, detection, if I recall correctly. It's well over 3. But we actually got the mass measurement. And just to be safe, the argument could be that, well, maybe there's something buried in there, or maybe you're just seeing noise and you're kind of seeing some correlated noise and maybe it's not real. The way we actually confirm this is we get Doppler tomography observations, which tell us something, first of all, something is actually occulting the star because you're measuring the shadow of the planet in the line profile. And I'll show you a clear image of how that works. But the radio velocities rule out the eclipsing binary scenario. So not only do we have a 3 sigma detection for the radio velocity curve, so we have a mass, it's about 3 Jupiter mass, but we know that it is actually occulting, there's something occulting the star, and so everything kind of works together. So what is Doppler tomography? What is this magic that I keep talking about? And so this is a great movie made by George Zhou at CFA. But essentially, you have your line profile here, and you're literally measuring the little dimple, the little shadow of the planet going across the star. And this corresponds right here to the shadow going across, and what this tells us is that this planet is actually moving in a prograde orbit. Now, this is not the system I'm talking about. This is not KELT 9. This is just another sample just to show you kind of how the technique works. But this shadow goes in a prograde direction, and this is what it corresponds to the planet going across a star. And again, it takes advantage of the fact that a star is not stationary. Part of the star is rotating towards you, part of the star is rotating away from you, and you take advantage that the planet actually covers up parts of different blue shifted and red shifted light. So, what did we do with KELT 9? We went out, we got that Doppler tomographic observation, and what we found out is that the shadow was not prograde, so down left to top right, but was actually straight up and down, which means it's in a polar orbit. Okay? And so this is the image, the movie of what the system actually looks like, and the planet goes almost directly down the center of the star. And what we know is, and this is where it gets really crazy in my opinion. So this is, again, planet host is very bright, it's a B of 7.5, so it's a very good target for atmospheric characterization. The temperature of the star is very hot, it's over 10,000 Kelvin, it's equivalent to an A0 star, right? So about 2.5 solar masses, 2.5 solar radii. And the planet is large. 2 Jupiter radii, 3 Jupiter mass. But what's really interesting is if you calculate your equilibrium temperature, what do you find? Well, the temperature is about 4,200 Kelvin. Well, that wasn't good enough. We actually went out and got secondary eclipse observations from the ground with a 1 meter class telescope, because the secondary eclipse is 1 millimag. And we get the actual day side temperature to be 4,600 Kelvin. Anybody know what star that would be? It's about a mid-K star. So this planet is hotter than most stars. And I thought that was absolutely baffling when I first saw it. And because it's around an A0 star, there's a lot of UV radiation coming out, and so you're actually blowing away the atmosphere of the planet, and this object receives by far more radiation. I think it was about like 700 times more radiation than any other planet we know about, as well as it's by far the hottest planet we've ever discovered by about 1,300 Kelvin. Talk about it just being odd. Well, you know, we're in the age of Twitter. Well, when Captain America takes some time out of his day of fighting crime to tweet about your exoplanet discovery, I think that was a highlight of my career. So as you guys may or may not know, Chris Evans is the actor that plays Captain America, and he actually tweeted about this, and we tried to tweet back at him and try to get him to like talk to us when he was too busy. But it was really great because it just showed that like the public was so fascinated with this object. So that's what I'm going to talk about for KELT in the sense of exoplanets. I'm happy I can show you, again, 24 almost planets and go through those cases. But what I want to talk about now is K2 and the work we've been doing with K2 to answer fundamental questions, to find systems that answer fundamental questions. So as you guys know, Kepler was a 4-year mission. I think it lasted a few days after the 4-year time, and then the second gyro broke. And essentially, it was not able to point at the location it had been pointing for 4 years with stability, and therefore they actually put the telescope in safe mode. Well, the Ball aerospace engineers are geniuses, because what they came up with this idea is to use the solar pressure to actually stabilize it and use it as a third axis, and therefore they could point across the ecliptic. They could do these 80-day-long campaigns, and their precision is very similar, well, it's a little worse, but similar to what Kepler was getting. So now you take a spacecraft, a very high precision photometry working workhorse that's done such great work, and you get to point it wherever you want along the ecliptic. That's the key. And so we've now confirmed over 140 planets from the K2 mission, and there are plenty more to come. We still have a few more campaigns. We'll be mining this data set for a decade. But one system that we found about a year ago is HD 106315. And now this is a multi-planet system. On top, what you're seeing is the K2 corrected light curve and flattened, and you can clearly see the transits coming down. What we found is there's 2 planets around this star, one around 9.5 days, the other one at 21 days, and the depths correspond to a super Earth and a Neptune. And what's interesting is it's the host star. So we're actually observing these planets around a mid-F star that is rotating about 15 kilometers per second. So using, one sec. So again, these planets are very small. These are, again, Earth-sized, super-Earth to Neptune-sized planets. But this is kind of the big point right here. Using that technique, Doppler tomography, is very difficult because of how you have to how the light gets spread out across the detector. So you need high signal and noise, but you also need a fairly big planet to cause the shadow so you can see the actual dimming. Well, what do you know? HD 106315c, the Neptune at 21 days, is the first planet, small planet, that's actually amenable to this type of measurement where we can get the spin-orbit alignment. And it's a very important measurement because it tells you about formation. If you assume planets form through some kind of high eccentric, dynamical interaction and they get shot in, then they should be in different orientations relative to the spin of the star. And therefore, you would expect to see kind of a uniform or maybe like a broad distribution. However, if they're all aligned, that implies some kind of smooth, slow migration, and therefore the planet probably just lost angular momentum and slowly migrated to where we're finding it. So by getting this measurement, we can actually answer these questions. This is a simulated observation using the 6.5 meter Magellan telescope with the Mike spectrograph. And what you can see is you can clearly detect the shadow with one observation. Now, I don't actually have the data to show you because we have not had very good luck, and at 21 days you get about 2 opportunities a year. So we have not gotten this observation. We have 2 opportunities this semester, and we hope to get this observation. And I hope to show you maybe it's misaligned or it's aligned, and then that will provide some evidence for one mechanism towards the other. The second planet system that we found is GJ9827. And I realize I'm just saying like catalog ID numbers here, but they are significant. But the reason this planet is so interesting, it's actually the closest planet ever discovered by K2. It's at 30 parsecs. So it's very close. It's very amenable to characterization because it's really bright in the infrared. But at the top, I actually did not, I'm showing you the uncorrected, so this is corrected for systematics, but this is actually the stellar variability of the star. And so we can see that the rotation period of the star, and then you can see the planet's transits going down. And then this is our flattened light curve with the model where we did a 3-planet simultaneous fit to get the system parameters. So if you zoom in and you phase fold all your transits, you get 3 transits. These periods are probably a little interesting if you think about it, because this is 1.2, this is 3.6, and this is 6.2. So there is a resonance here. And what we find is that we have 3 planets, all super Earth in size, and that they span a very important radius regime. And I'll get into that in a second. So the interesting thing is, because of the period of these planets, they actually simultaneously transit. And so you get to make these really pretty images in movies where you get to see the planets kind of racing across and you can see the different light curves. And just to give you another one, right? And so, in addition to it being very close, in addition to it being the opportunity to observe simultaneous transits, what is really interesting is this last point. We are actually spanning the rock to gas transition. So we know at 1.6 Earth radii, there is a clear dichotomy of exoplanets in size. And what we find is that most planets are either around 2 Earth radii or lower at 1.2 Earth radii. And so B.J. Fulton discovered this kind of dichotomy by looking at the Kepler sample, getting improved stellar parameters through spectroscopy and different types of techniques, and found that there is this clear dichotomy, and the center is right around 1.6 Earth radii. And what we realize is that all the planets out here are gaseous and have a thick hydrogen envelope, and the planets that are smaller don't have an envelope, don't have that thick gaseous envelope. But the question is why? What is going on at 1.6 Earth radii that is causing this clear difference?
Can I ask, what do you mean by the radius of the planet? I mean, if you count the atmosphere, you're counting just the solid part.
So we don't know the difference. When we observe these things in just the broad optical light, what you're getting is just the relative size of the planet, which includes the atmosphere as well. So all we see in these discoveries is what we think the planet radius is, which is accounting for the atmosphere as well. When we go and get follow-up observations to understand the atmosphere, that's when we realize most of the planets right around this 2 Earth radii have hydrogen envelopes. Also, they're less dense once we get the mass, so you can tell they're puffy. And the planets lower than that are rocky and dense, and we can't detect atmospheres of. So that's kind of how we know the difference. But we're only getting one measurement for radii. So we're not, it encompasses both the planet, the actual rocky part, as well as the atmosphere. Same thing for the gas giants. Is there another question?
So this is taken from all host stars?
Yeah, so, and they actually did look at this. This is including all host stars. This is the entire Kepler sample. But they did look at stellar types, and it does change in significance, but it's still there.
Yeah, because you expect like hotter stars to blow off our the atmospheres.
You would, except if that's not what's actually going on. If what's actually going on is there's just more mass and they're able to hold on to it, there's not a big difference in the sense of the actual radiation of the star. It may be the actual just gravitational force on the planet. But you're right. These are things that they did look at, and that dichotomy just still remains. Now, the interesting thing about GJ9827, as I lost track a little bit, if you plot the radii of the 3 planets, well, one ends up right before the gap, one ends up right in the middle of the gap, and one ends up right at the end of the gap. So you have 2 planets that bracket this dichotomy, and one that lands right in the middle. Therefore, you can keep the star constant in your experiment now, and you can study these 3 planets, and you may be able to disentangle why one planet is larger, one planet is smaller, and what's going on with the one that's just sitting in the center. So again, we're finding planets that allow you to answer key fundamental questions about planet formation and evolution. Now, what's the future? Well, the future is bright, and I realized the pun there. We're about 8 weeks away from the launch of TESS. We expect TESS to be just as impactful, if not more than impactful, than what Kepler did. We're expecting 20,000 planets. But we also have James Webb that is going to come up online and hopefully launch in the next year and a half. And so, with these 2 facilities, we are really going to be able to expand our knowledge of exoplanets and planet formation. And specifically, TESS, because again, 20,000 planets, and a subset of that will be around the brightest stars in the sky. And again, the idea of TESS is to find and measure the masses of small planets and try to understand the density of small planets. And additionally, we will find thousands of other planets that are interesting for other reasons, like long period planets that can answer fundamental questions about how giant planets form, how they evolve, how they migrate, things like that. Additionally, the James Webb Space Telescope is also going to answer key questions about atmospheres. They're going to study the atmospheres of these planets. The planets that I've talked about today are top targets for JWST. I realize that this last point, some people don't find it as great as I did, and I understand why, but we actually, the exoplanet community came together, put in a big ERS proposal, and was awarded 25% of the JWST cycle 1 time. That means that we have a very big commitment to the community to ensure that we get as much out of this data for developing tools and analysis techniques for the future cycles. But that kind of showed the entire community came together for this. And the big thing I want to point out about TESS is that you don't need big telescopes and high precision spectrographs to do TESS follow-up. TESS is going to need a lot of people to do follow-up, to rule out eclipsing binaries, to observe targets just to confirm that things are actually happening around the right star. So small aperture telescopes, again, like the facility up top, would be great to follow up TESS targets. And in fact, we are transferring our entire network to do TESS follow-up once it launches and starts delivering candidates in the next 8 months. So, how am I doing? All right. So with that, I want to kind of change gears a little bit and get away from exoplanets and actually talk about planet formation. And what I like to study to try to understand planet formation is called occulting disks or eclipsing disks, which is literally when a young star gets occulted by a portion of the circumstellar environment, whether that's part of the disk, whether that's just planets that are forming that are more of a dust clump than they are actually a planet at that stage, or whether there's material around some companion in the system, some other star, that's actually occulting it. And because you actually, when you get these occultations, you actually probe the size of these dust clumps and start to understand what's going on around that system, and you can timeline how planets form over, at different ages, because you can look at systems of different ages. So, this was the DESK survey, the Disk Eclipse Search with KELT. It's one of those acronyms you make as a joke and sticks. It's now published in like 10 papers. But the idea was that there's this sample of over 3 million stars. In fact, we're at 4.5 million stars that are available for the KELT survey. And we were looking for large occultations, large dimming events of young stars, trying to see if we could find these disk eclipsing systems. Now, this was an original collaboration with just KELT, but the Assassin team, the WASP team has also joined this effort. And this is based off of the discovery of J1407, the first circumplanetary disk system. So they found this 4 magnitude, about 60-day long eclipse. Yeah, 4 magnitudes is a lot. Right, this thing almost goes completely away. And what they figured out was by modeling the different features, the different structure of the eclipse, that they could fit a eccentric ring system around a substellar object that was consistent with the actual photometry and the variability, and you would just have different rings, different opacity changes that would correspond to the variability during the eclipse. This is also inspired by Epsilon Aurigae, which is a 27-day eclipsing binary that is a 1 magnitude deep eclipse that lasts, I think, 2 years, if I recall correctly. And it's caused by a F giant being eclipsed by a B star with a disk around it. And that was the theory until 2010, when Brian Kloppenborg published a Nature paper using Chara imaging where you actually see the disk shadow go across a star. So this is the actual Chara imaging over time. And therefore they confirmed the idea. So the idea was to find more of these objects. And the first question was, could we even find, are there any more to find? Could we actually find them? And we got a quick answer of yes. In fact, the first time I ever ran the search algorithm, a young star called RW Aurigae came out and showed this about 2 magnitude, 180-day long eclipse that we had no idea what it was caused from. Now, what's great about ongoing surveys like the DASH, the photographic plates, the AAVSO, the American Association of Variable Star Observers, these amateur professional networks, is that we can go back into their database and dig out 70 years of photometry and understand the history of this system. And so we went back, and I see that there's a lot of baseline changing and there's a lot of variability in structure, but there is no event that is similar to what we saw in 2010 for the previous 60 years. Okay? Now, I've already hinted there's been a few more dimming events, and I'll show those in a second. But what's interesting are the last 2 points. And we went in and we found millimeter observations. These are on the left, where these are 12 CO observations of the RW Aurigae system. And what we found out is, and we're continuing to find out, is the more we dig into this object, the more complicated it gets. I think that's kind of the beauty of science, but it's also the most frustrating part when you can't get an answer. But what you see here, the center of this cross and this cross are 2 stars, RW Aurigae A and B. Each star has a disk around it. These disks are about 30, 40 AU in diameter. And then what you're seeing here is a large tidal arm of gas that's wrapped around the star, and it's actually trailing after the B component. And what's interesting is, if you look at simulations of a star-disk encounter, essentially where an eccentric binary comes in every so often, maybe within the radius of the original disk, it'll tear up the disk, and then what you see is the aftermath of that interaction, which is this tidal arm, which is very similar to what the simulations show. Now, maybe turn your head a little bit, maybe back, maybe, squint a little bit, but what you see is that the structure is quite similar. And I think that is the key. And so that gave evidence of what is going on with this system. And so this also promoted from the occultations, because they didn't know about the occultations in 2006. This promoted new simulations. So this is just an n-body simulation. These colored points are points that are not bound to the system. You can kind of ignore them. And what you'll see is there's a star here. This is RW Aurigae B. This is RW Aurigae A. This is the original disk. And you can see what happens. So you get this nice large tidal arm around A. You get this kind of bridge of material. And B runs away and takes a bunch of the material with it. Well, this is nice. Right? It gives kind of an answer, or it gives a new answer for this specific system, but it's not a confirmation. And so what we did, skip one step, I wanted to show you that this thing has gone crazy since the 2010 occultation. In fact, prior to this, there was no event for 60 years. It dimmed in 2010. There's a small dimming in here that's a little tough to see. And then it dimmed again for twice as long, a little deeper, went back, dimmed again, and it's actually in a dim state right now. So we don't know what's going on, but for 60 years it did nothing, and for the last decade it's gone through 5 different occultation events. So what do? Well, you have old millimeter observations, you have some weird system, you know there's a lot of material. You go out and you try to get ALMA time to try to see if you can really probe the structure of this system and maybe tie the photometry to the actual architecture. And I think that's the key point of my research, because photometry is inexpensive to obtain, ALMA is incredibly expensive to get. If you can understand architecture of a system from the photometry, it's much easier to get the time to get that observation than it is to get the ALMA observation. But you have to prove it. So what did ALMA show us? ALMA, like I said before, the system just kept getting complicated and more complicated the more we dug into it. So again, you have your RW Riga A. This is a disk. I don't have the moment 1 map, but we have clear rotation in the disk around RW Riga A. This is B. There's also clear rotation in RW Riga B. It's the first time it's ever been resolved. And this is the original tidal arm. And what you can kind of see is that tidal arm seems to be a small part of a larger structure of a possible circumbinary ring. Additionally, you see this kind of third source in the center. Well, it's not actually a star. There's no Keplerian rotation. There's no suggestion that it's a star. And what we think this is, and this is a little tough and a little tricky to visualize, but we think that this is actually a second tidal stream. And what you're looking at, this third source, is you're looking down the barrel of that stream. And so what does this tell us? Well, this means there's been more than one interaction, right? Because you cannot get this configuration from one. Therefore, it's probably, first of all, it tells us the binary is bound, which is interesting because we didn't know that. And two, it tells us there's been multiple interactions. So this is in prep. I'm hoping I circulated the paper. I'm hoping that's going to be submitted in the next few weeks to a month. Now, my last system I'll talk about, am I doing out of time? I think I'm fine. Is actually not a young star, but it's one of our bigger discoveries that we've gotten. And this is an M giant being eclipsed every 69 years by a small hot companion with a disk. And I'll get into the details of this, but because of the dash photographic plates, we have 120 years of photometry. I mean, I have to say, 120 years of photometry, that is spanning, a time frame where we can start to understand phenomena on century-long timescale, something that we've never been able to do. But because of things like DASH that have continued to go, even when funding has been struggling, and they have not been able to fund this, they continue to do these observations, and we're able to use those observations now and still pull out really interesting science. So this is the 120-year photometry. This is the zoom-in of the eclipse. Unfortunately, this is very faint for KELT, so a lot of this is upper limits during the eclipse. But you can kind of see the yellow and red points, and those are Saturn and Catalina, and they clearly see this 4.5 magnitude deep eclipse that spans 3.5 years long. Now, when you find these weird things, the question always is, what is causing them? And so what we did, and the bottom here is just a phase folded to 69.1 years. And we removed the KELT data, and you can see that the eclipse and the model line up very well. The beginning of the eclipse, the newer eclipse, doesn't line up very well with the previous eclipse, but it's very possible that the disk structure has evolved in a 70-year baseline. So what do we know from spectra? We know that the primary is an M giant, so this is an evolved system, post-main sequence. We know that the companion is hot, and the reason we know that is from the SED, so this is a little complicated, but the top red curve and these 2 points out here, UV, these are all out of eclipse, but because the eclipse lasts 4 years, you can get observations in eclipse too, so we actually create 2 SED models, in eclipse and out of eclipse. They're consistent with each other, just reduced by a factor of 100, or 1,000, sorry. But we know that the UV points don't come from an M giant. M giants don't produce UV in any way. So that must come from the companion. And then if you fit a quick black body, and it's a little tough with 2 points, but what you get is an estimate of the temperature to be about 8,000 Kelvin. So that's interesting, but we don't see any sign of it in the optical, which is weird. So if you take, so again, I mentioned the depth and the duration. If you take that duration and just make some assumptions on the size of the star, what you get in the period, you get Kepler's laws, you get a velocity of the object. This occulting body has to be about 1 to 6 AU in width. So it has to be huge. The disk system has to be gigantic. That's understandable given the size of an M giant being about 100 solar radii. Now, interestingly, if you take the two temperatures, Stefan-Boltzmann law, right, you can get a size of the occulting or of the companion. And what we find is that the companion has to be between 0.1 and 0.5 solar radii. Now, that's a very interesting range because if this is 8,000 Kelvin, it can't be an A star, not at that size. Also, we would see it in the optical because A stars are incredibly bright. But it can't be a white dwarf because it's too big to be a white dwarf. And that would be the other idea. So what actually is going on? And so what we think is going on is that this is a sub-B dwarf. Essentially, you had two giants, red giants, through some interaction which we really have not been able to explain. One of the red giants was stripped of its outer layers, which has created a disk around that companion, and what's left is that hot core, and that's what we're seeing. And that's currently the interpretation. Now, the beauty is that this is periodic, and it will happen again in about 60 years. And so what I'll say is get your telescopes ready, start planning now. You don't have a whole lot of time, but I hope that when I retire, they'll confirm my interpretation, and I can kind of leave on a high note. Or worst case, they get cited in 60 years. So, also, this is a Guinness World Record. I thought it was actually a joke. The person who emailed me was like, oh, we'd love to put this in the Guinness World Records. I was like, ha, that's funny. And then I looked at the link at the bottom and I checked it out. Corinne Burns is an editor for the online journal for the Guinness Book of World Records, and it has its own record. Now, don't congratulate me because the record does not go to me or my team. It goes to the star. And so I actually was going to ask, like, do you guys like send a plaque to it, like? Just let it go, but I figured I'd already pushed my luck a little bit. And so this is our really interesting system. Although it doesn't really answer the question of planet formation, it does bring up another question. If you have this material around some evolved system, and we know of pulsar planets, they were arguably one of the first planets discovered. What about the idea of reinvigorated planet formation? Post-main sequence planet formation. Could you actually form planets out of the material that's left? It seems like a little bit of a stretch, but given that we are seeing material around evolved systems, given that we found pulsar planets, which we don't really know how they would have survived a supernova explosion, could you actually have planets that reform or form in the post-main sequence age? This is an ongoing question, and the idea is to find more of these systems to see if maybe we actually find planets around these types of stars. Now, I have a few slides left, and I just want to highlight some work that my students have been doing. This is Jack Lubin. He's actually left the industry to come back to graduate school. I'm so proud as an advisor. But Jack actually did a really interesting project that we thought was not feasible in KELT. KELT only goes down to about V of 13 or 14 with that, maybe upwards of 5% type photometry. However, we thought maybe we could try to look for eclipsing binaries, so low mass eclipsing binaries, because the eclipse depths should be hundreds of millimags because the stars are relatively the same size. And we wanted to do this because, as maybe some of you know, maybe you don't, but the radii of low mass stars are not properly modeled by current theoretical models. Essentially, we underpredict the radius by about 10%. Yeah. And so what we're seeing is a 10% inflation in radius, and we don't understand why. We think that this could be due to magnetic fields, but there's only a handful of these systems. And so by discovering more and really getting precise mass and radii, we can actually start to understand which models are doing better and what those models are doing that distinguish them. And maybe we can find out what's actually causing this discrepancy. And so he looked through about 2,000 targets. He ran a big Ohms-Fargel, BOS, and AOV search. He actually went through about 100 or 200 of these by eye, developed candidates. We had the follow-up team follow up these candidates. So these are the follow-up observations from the KELT follow-up network. Here's the original discovery light curve. And then we got radial velocity from the YFES 2.4 meter from the Australian National University. And just using facilities, low-res spectroscopy, small aperture telescopes, we were able to confirm a new eclipsing binary that is around a very bright star that'll be amenable for characterization. We didn't get them down to like 5%. That's the limitations of the facilities. but we are planning to follow the system up with high-res spectroscopy, and the hope is to pin down the mass and radius to about 1%, like they've done for a few systems. Additionally, Emily Rowland also worked with me while she was an undergraduate at Vanderbilt, and she looked at TW Hydra, a known moving group, and did a rotational analysis. And one of the ideas about this was that you could confirm, or you could suggest membership based on rotation period. Young stars should rotate very fast. They should be rotating less than a couple weeks. So if you find a young member, a moving group member, that's say rotating with a period of about 30 days, well, that's probably not a young star, and therefore it's been misclassified as a member. And knowing the memberships of these moving groups and these clusters is very important because that tells you the direct age of the system, one of the hardest things to measure in astronomy. And so she did this really nice rotational analysis of TW Hydra. This paper is in prep. We hope to have it out in the next few months. She's also going back to grad school after a few years of leaving. Both my students worked at Capital One Bank. I don't know why I was recruiting for Capital One, but you know, take what you get. And so these are two of the examples. This is actually a clear rotation period. This was actually a contact binary that we found. And the idea is that we're probing this 10 million year old range, which is not really probed by many other clusters and not as well studied as TW Hydra. And so this should really help us understand the membership of TW Hydra. And possibly going forward, we're going to do all of the moving groups with KELT, with TESS at high photometric precision, and therefore dig down and get rotation periods for a lot of these lower mass stars that are just not accessible from the ground. So this is just kind of the first phase, but we expect this to continue. So with that, I'll kind of quickly just wrap up. As I mentioned, we had the KELT survey. It's actually observing over 70% of the entire sky. We found a few dozen planets almost. We have a couple more good candidates we hope to kind of confirm. We've been finding planets around massive stars, which is kind of a new regime, and to the point where we now have enough to start to put together some demographics. And what we're finding is that they're all misaligned, all of them. Additionally, we're using K2. K2 is allowing us to kind of look at smaller planets, but still answer fundamental questions. And this is kind of going to be the bulk of what we do with TESS, is finding these rare, valuable targets that allow us to answer some specific question about planet formation or evolution. In addition, I've been running this desk survey, which we plan to continue in the era of TESS, but the TESS baseline is not particularly long enough for us. But LSST will be incredibly powerful for what this survey will find. In fact, we expect about 100 of these discoveries at least from LSST. And again, just to remind you, TESS is going to find 20,000 planets over its lifetime, and that's just the 2-year nominal mission. The expectation is that TESS will get about 10 years of running, and the lifetime of the spacecraft, I heard, is a century, because the orbit is so stable. Now, I just want to end with one thing. I've heard a lot about supernovas since I've been here for the first few hours, and I think a lot of you guys are going to be surprised, but KELT can do extragalactic science because of M82. And so, as you guys probably know the story about the M82 supernova, it was actually found by someone doing a public night. I don't remember, I think it was Belgium, but I don't remember exactly where. And they were doing a public observing night, and they looked at M82, and they're like, well, that's not supposed to be there. And then they informed it. And so it was actually missed because it's saturated in most of the other ongoing surveys. But what's really great is we went back, and due to the position of the moon, due to various other things that we can't really, just weather and how we do our observing, we were actually getting 30 observations a night leading up to the supernova. And so even though the first detections were, I think, about 3 days past, we went back and we actually had first light. And so we had this nice, beautiful supernova curve. None of us know a whole lot about supernovas, but we worked with a team, and apparently this was very informative because they didn't have first light of this thing. And just to end it, KELT, little 42 millimeter camera, doing extragalactic science. And with that, I'll take questions, and thank you for your time.
Thanks very much. Question? Rob?
Oh.
Is there an explanation for that one transiting planet that's going perpendicular to the rotation axis of the parent star?
Yeah, so I mean, it pretty much argues that this had to have formed through some dynamical interaction. So it was probably kicked into where its current location is, and it probably didn't go through the typical migration where it just kind of loses angular momentum slowly. So this argues that maybe it didn't even form in the system that it's in, and maybe it did.
How big is that planet?
It's about 2 Jupiter radii.
So you're keeping it Jupiter radii perpendicular to the open plane.
It's tough, but this is where the dynamicists and the theorists are really having fun, because they got to try to explain this now.
But is that stable?
Yeah, it's stable as far as we can calculate forward, but the lifetime of an A star is not particularly that long either.
Actually, yeah, so, I mean, A stars usually are fairly rapid rotators. Do you know anything about the rotations?
Yeah, so it's rotating at 130 kilometers per second.
So, I mean, rotation distorted. Does that do anything to light curve? Or?
It does, but it's so new that we're not accounting for it properly. So our radii estimates are actually underestimated due to the oblateness of the star. But it also depends on the orientation of the orbit. And so we don't actually account for that. So we do explain that in the paper. But unfortunately, it was just kind of a new thing that like our current abilities to globally fit these don't account for the actual oblateness of the star.
Do you see you don't know where the orientation of the star is? It's rotating.
No.
So you don't see any spots or anything like that?
No, and A stars don't typically have spots.
So planets like Jupiter and Saturn, they have auroral emissions. They have auroral emissions. So when will any of these exoplanet telescopes start being able to see any signatures of auroral emissions?
Wow, that's an interesting one. I don't know. It's not something I've ever really thought about. Hopefully soon. Yeah, I think that would be really awesome to detect. But I don't know I don't know if they're kind of continuous. I don't understand. I don't know a whole lot to really answer that question. But if they could, and if they find a way, my hope is they do it, because that sounds really cool. But I don't know the answer. I'm sorry.
I have a more sort of general question, which is you talk about finding these planets around bright stars that you can characterize really well to help you understand planet formation and some different questions that you can answer. What do you think is the most interesting open question that you'll be able to do with these test planets in particular, or follow up with the KELT one?
So I'm actually, I plan to help out with the level 1 requirement. And so for those of you who don't know, level 1 is to get 40 super Earths, get the masses of them to understand the density and understand the composition. I plan to assist in that effort, but I'm more interested in actually understanding long period planets. As as all the way in the beginning of the slide, but as I showed in the beginning, we really haven't probed past about 100 days, and really like that's kind of really the limit of what Kepler was able to do. And that although TESS won't be able to do much, we also haven't found a whole lot of long period planets because we looked at a very small part of the sky. So my hope is that we'll find longer period, kind of warm Jupiters on the periods of 10 to 100 days. We only know of about a dozen right now, and if we can increase that sample size to 3 dozen, start doing spin-orbit alignment measurements, right? Compare that to the hot Jupiter population, you can start to understand whether they're migrating and warm Jupiters are just precursors of hot Jupiters, or whether they're actually forming where we're finding them, which would be groundbreaking because nobody ever thought that Jupiter-sized planets could form at a few stellar radii from the star. So that's one of the big questions, but there's going to be so many questions. I couldn't really pick a favorite. It's just one that I think of off the top of my head.
Any more questions? All right, well, let's thank Joey again.